Start the recording. All right, so we are moving on to ETG. Again, we're going to sit down with Shell and see if we can put a small slide for the discussion, because we owe to Maria, I think, for the presentation. So now we have ETG, as you know, again, ETG, in short, is the new stuff, right? Like the next frontier. So we are inviting topics that don't naturally fit into one of the existing projects that you heard already. And first up, I think we have Avinab, right? Can somebody double check? And then we have Matthias. And again, I had the typo yesterday, where as I was rushing, I put the wrong presentation, but we now have Avinab first, who'll talk us about avatars, right? And then we have Matthias. Avinab, the floor is yours. Let's try to stick to the schedule.
Yeah, thanks, Yannis. Just wanted to verify you guys can hear and see my screen in the presentation mode.
Yes, we can. Go ahead.
Okay, perfect. Yeah, I'll try to stick to the schedule.
And maybe, sorry, let me just say, we are welcoming Dr. Avinab Saha, who recently defended his thesis. So go ahead.
Yeah, thanks, guys. Hey, hi, everyone. This is I'm fortunate to be here and giving my talk at ETG at VQEG. So today I'll be presenting. So first, some intro about myself. I am Avinab, and I recently completed my PhD at UT Austin, working with Professor Alan Bowick. And today's topic will be about evaluating subjective expression differences in human faces. Okay, so this is this from our very recent work from SIGGRAPH that is going to be coming out later this summer, and this is a joint work with our friends at Meta, including Yannis, Christian, JC, Alex, and of course Professor Bowick and Yuchi from UT Austin. So as you know, digital human renders are widely used in different social media, entertainment, and different kind of applications. But and they give us a lot of photorealistic face avatars enabling immersive interactions. But how do we ensure that these representations are perceptually accurate and convey the intended nonverbal signals? And how do we measure these perceptual expression differences is a critical task that we want to understand. As we know, the existing difference metrics like mean square SSIM are not mean square error are not perceptual, and as well as SIM kind of metrics focus on low-level image or geometric features, and they don't really capture the unique meanings which are imparted by the expressions. So developing a perceptually aligned expression difference metrics is definitely desirable, but probably challenging due to the lack of subjective databases, and which can be used for training and validation, validation, of course. So in this work, which we introduced a new dataset called Face Expression 70K, is the first large-scale dataset on perceived expression differences. And in this work, we also benchmark a couple of existing metrics and try to show some direction about what kind of metrics might work going ahead for this kind of tasks. And we also have some applications around how can we train improved expression difference metrics, and some predicting some thresholds which can be used for latency related applications in VR. Now, so to construct this dataset, we use the multi-face dataset, which is an open source dataset from Facebook, and it contains a lot of high resolution facial images. And it's captured using a setup that you can see on the right. It has 40 camera setups. You can see from all the directions, and the faces are captured, and it includes people doing different kind of face expressions. There are more than 60 of them, including the subtle and the nuanced variations. The good thing about this database is it has pretty much controlled lighting conditions, so we can understand, we can study face expressions and properly without interference of other factors. However, this dataset actually provides recordings of face expressions from peak to neutral, and we will sample these video sequences to generate our pairs of face expressions that we will use in our study. And I'll come to that how it is done later on. Now, for our study, we use around 61 unique expressions spanning a gamut of emotions, as you can see on this slide. And we sampled from 8 different actors representing some sort of diverse representation that we could do with obviously the scale of the study and everything like considering, and what is available to conduct a study like this where we want to study different kinds of face expressions in very much detail. So with this, we have this actors in our study. Now, as I said, like we are using the multi-phase dataset, which is a video dataset of recordings of expression transitions from peak to neutral, but we want to really sample a few frames of images which show us different kind of expressions. So what we do is like we use the quest procedure, which can be used to actually get some thresholds of perceived expression differences. So we start off by choosing the peak expression and the neutral expression shown by the the circles in 1 and 2, and then we try to get one JND samples from the peak towards the neutral and from the neutral towards the peak using the quest procedure. And once we have this 3 and the 4th, we just choose a sample in the 5, the middle point in the 5. So in this way, we are able to generate like 5 sampled frames, which are somewhat perceptually different, so that it's meaningful to consider them in our subjective study. The reason that we don't use uniform sampling is because like the dataset is constructed in such a way that the peak and the neutral expressions are kind of held constant for a long period of time. So if we do uniform sampling, it's possible that we just generate data that is not really relevant for our study and might have a lot of redundant data points that will trivially result to 0 expression differences. That was the motivation of using this sampling procedure. And we use like around like 462 expressions across 8 actors, which gives us like 462 sampled sequences. Yeah. So once we have this, we can create our pairs of expressions. We have two types of expression pairs. One is an intra-pair expression, which is like when you sample expression pairs from a single expression transition. And the other is like an inter-paired expression where you sample expression pairs from 2 different transition sequences. Now, to actually explain to further explain this, like you have this intra-pair expression sequences where, as I said, from the sampling procedure I just described, we have 5 expression sequences going from the peak to neutral. And because we have 5 and we do like a pairwise comparison, we get like 5C2, which is like 10 pairwise comparisons. And for inter-pair expression, we try to reduce the size of the data because like neutral points are kind of trivial. So we just choose like 3 out of 4 of the non-neutral frames, and we get like three frames per expression. And we do just a pairwise for every pair of expressions to give us like 9 pairwise comparisons. So once we have something like this, we conduct our subjective study on Amazon Mechanical Turk. So our data set is like around 70,500 expression pairs, out of which you can see like 4620 is intra-pair expression and almost 65K is inter-expression pairs. Because this goes quadratically, the size increases. Now, we collect like we recruit around like 1,021 workers on Amazon Mechanical Turks and get around 32 ratings per expression pair about how much is the expression difference, followed by like a very standard procedure of using P910 to process the scores to get the histogram of the expression differences. And as you can see there, it's slightly skewed towards the higher side because as you understand, like because we have a large proportion of inter-expression differences, like those like try to be on the longest, like the highest side of expressions. Now, this is like our study interface. We use this interface for our study where the user could basically slide. It's very similar to a Likert scale that we have been using traditionally for image and video quality assessment studies. And we have the scale, and we actually like do whatever is like very standard in this field to educate workers how to do the rating. And then we also like catch like the people who are not very you cannot trust them. Like we have some measures like that to catch people who are not very attentive during the study. So with all this in place, we are able to do the study, and we get like around like a very high inter-subject correlation of 0.91 with our monitoring techniques and stuff. So like the data that we collected, we feel is pretty robust. So this is like a sample annotation for 2 expressions that we have. So like there are 2 expressions, one on the top and the one on the left. So on the right, you can see like the intra-expression differences. This is basically a lower triangular matrix. It could be a square as well, but like the the numbers would be same. So it's a lower triangular matrix of lower triangular matrix of the scores on the top, and the bottom you have the inter-expression difference scores. Why we have some of the numbers crossed out is because, as I told, we are like using 3 out of 5 frames per sequence. So that gives us around like 9 numbers which are there in this plot. So once we have this, we can actually go around and do some analysis about the data. So the first thing is that like very simple things. We are just trying to understand how the peak expressions, like for different expressions, how much is the peak to neutral expression difference across different actors and also across different actors. Now you can see on the x-axis we have different expressions, and the y-axis we have the perceived expression difference scores, and the black crosses are basically denoting each actor. Like we had 8 actors, so we show those values of those 8 actors, and the blue symbol basically shows the min-max range of that. As you can see, like for some of the expressions, the perceived expression difference across the actors can be really high, while for some they can be really small. And like this is like a visual representation of that. Like on the top, you can see that the expression difference between 2 actors is quite high, but on the lower side, like on the top, it's like 48 versus 4, and on the left, on the bottom, the other expression, the numbers both are in 70, so they're like really tight. Also, because we are conducting the inter-expression differences, we could also compute the average inter-expression scores across the actors, and we can do a lot of processing around those to get different clusters of perceptually similar expressions. So what we did, we computed the inter-expression scores for every pair of expressions, and this is a big number because 60 expressions, and this pairwise too is like around 1800 pairwise numbers that we have. So we wanted to show this in like a plot, like, but it's probably the best way we can show in a like a limited screen space. So we also like clustered them, and we are just trying to color code them just to see how perceptually similar expressions can be grouped together. And this is also like shown because like towards the diagonal of the triangle, you see that they are like generally the greener or the yellow colors, which mean that the scores are like kind of lower on the diagonal, and on the other parts of the triangle, it's like higher side. So it just also shows that our study is kind of successful in getting the perceptually closer expressions together. So this is also like a very similar plot like this. Like you can see for the top pair of expressions, the difference of expressions is very high, but for the lower plot, it's very small. So everything just shows that like this is a perceptual nature of the task, and there's no straightforward like something like a mean square error that you could do to get the expression differences. We also show that like the expression transition dynamics can be very different across different actors and expressions. On the left, you can see for like 5 expressions, we fix the actor, and you can see the transition dynamics from the peak to neutral is very different. On the right, we fix the 2 expression and vary the actors, and you can see a similar trend. Like none of them is very deterministic. So like we need to have like perceptual metrics which can actually help us find these differences. Now, coming to the image similar, like these were all like some things that we could get from the data. Now moving on to the quantitative metrics, we very first like tried to use some image similarity metrics, both perceptual and non-perceptual, and try to see how they work. We find that they are not really great. Like LPIPs might be slightly better among the ones that we tested, but its predictive power is still weak. Now we move to the feature-based models, typically using deep learning models. We don't train models here. We are just evaluating everything in a zero-shot fashion. So we just take the features from different pre-trained models, popular ones like Resident 50, Moco V2 Clip, and there's also one face-specific multimodal model. And we just take those features and try to do some zero-shot cosine similarity or L1 distance and try to see how they do. So interestingly, like if you have these deep models, the performance really goes up quite a bit. Like you can achieve around like 0.77 SRCC, which is like decent considering these models are like evaluated in a zero-shot setting. So this is like just shows that we can probably explore more using deep learning models to come better on this. Now, going forward from zero shot to like maybe like some sort of like regression based tuning. So what we do, like we wanted to show that how can the database be used to improve this. So on the top, you have this like zero shot setting where we take this features from a deep model and use L1 distance, and we get around 0.7 SRCC, 0.773. Now, what we did is we used the features and just use the SVR regression that we have been traditionally using in an image quality, video quality setting. And we see that like we get around like 5% boost in SRCC just by this trick. And so we are also working on something like an improved model for this, which will be coming out soon. So we have much better performance. Like using deep networks, we show that we can reach around like 0.87 SRCC. So I'm just not including that in today's talk, but we have some models that we are building that can actually improve these performances. The another application, I think I'm running out of time, so I probably will skip it. So the gist of the application is that we can actually use our data set to compute the just noticeable differences for expression threshold. So as you know, in VR application, when you are batting a head-mounted display that is tracking your facial expressions, you have to like sample very densely to prevent you have to sample to prevent any lags, right? But this also comes at a very high power consumption and processing power. So what if we could predict those JND values and only sample just at the boundaries of those intervals? In that way, you can actually save a lot of power. So using the data that we collected from the study, we showed that like we can use like a 90 FPS like sampling actually avoids all perceptual expression differences across expressions. And also you could do some actor-wise fine-tuning to reduce that. So I think like once the paper comes out, you guys can have a look if you're interested. And yeah, I think like that's mostly it. And so as I said, like we are trying to improve this expression difference predictors. We have something in the pipeline that will come out soon. And the major application that we think that will help this is like the codec avatar training pipelines. Typically, they use MSE and LPIPS loss, and we saw how bad they perform on the subjective data. So we feel that like once we have like a good metric out, this could actually enhance the codec avatar training pipelines and actually develop this field further. And also, like, as a side application, I think like we can also explore something like expression transfer between different face avatars. So something like this could also be useful. Yeah, I think that's about it. I think thanks for listening and happy to answer questions.
Thank you. I see someone. I took your role just because you're on a hair, but please go ahead. I think we have time for maybe a question from the audience.
Yeah, sure.
Or remote.
Yeah. I mean, first of all, I want to thank you, Yanis, to taking over that. And I think it's better if you can continue that because you are here in the room. As for me, is probably like it can. I might lose my voice and all these things, because of the internet and all these things. But I think I appreciate that. So first of all, so
thanks, Simon. And again, anybody has questions? I see Patrick, the usual suspect, as I call.
Sorry?
The usual suspect.
Yeah. So first question of the day. Thank you very much for the presentation. So it's somehow related to one of the projects we are leading with few people in Europe, but also in Asia, so-called AC Mod project, affective computing modeling. So in that particular project, we are interested in of two types of expression, macro and micro expression. So I was because you are dealing with let's say some kind of a still image for the pair comparison stuff. How do you see the things for micro expression? And especially, it's well documented in the literature, especially in psychology, with action unit of the face, especially for micro expression. And this is something more related to temporal dimension. And this is something I don't see much in the experimental setup here. So it seems that we tend to lose the temporal dimension. Could you comment on that?
Yeah, sure. I think like we have been like thinking about that, like moving from static just face images to videos, because when we actually like train codec avatars, we eventually want them to be like temporally coherent and without any kind of like jerks in between the reconstructions. So that's definitely, I think, the next step towards it, and I think someone will be working on it soon. Yeah, so I think it's really important, like because but typically even the codec, yeah, sure.
So just want to drive your attention that there are already existing data set on the things. Can you go back on the slide where you have the actors?
Yeah, sure.
Oh, if I remember well, there was, okay.
Yeah.
Because okay, one drawback that we can see in existing data set is lack of diversity, and as you have shown in your result, there's a bit a lot of let's say standard deviation. The actor effect seems to be very important for the subjective test. So I'm just wondering if these 7 actors is enough in terms to diversity and so on. This is actually one of the focus of ACMOD. This is why we have Indonesia, Malay, Chinese. So to include, let's say, to increase the data set in terms of ethnicity, especially because you are targeting deep network, and they can be easily biased based on the data sets that you are producing. And so, any comment on that? Do you plan to expand?
Yeah, definitely. I think that's a really a good direction, and I think like computer vision algorithms traditionally have been biased by the race of the people. But at this point, I think like we are trying to like we can only work with the data sets that are publicly available. And I think like out of the publicly available data set, multi-phase turned out to be the best thing that we could use at this point. And obviously, I feel that as we have more faces, it might just get better. But however, I'd like to like draw your attention to this part of the study where like we showed basically when we do a 80-20 split, we are basically just trying to show the performance on like training on some subjects and testing on the other. Although it is not like a very strong check on whether like the diversity is checked or not. But I feel that even though like the transferability skills of the models that you build on this it's not great, but I would say it's decent. It's not very bad when we get a 0.8 SRCC on a train test split. So yeah, but I feel that I haven't like really explored that like the aspect in quite detail.
Thank you. And again, apologies for maybe stopping the discussion. Thank you, Patrick. Thank you, Avinab. And,
yeah, sure. Thanks.
We're moving on to Matthias. Matthias, are you ready?
Yes, I'm starting to be ready. Here we go. Oops. Okay. Where's my screen share button? Here we are. Okay.
And I really appreciate your help in getting us stay us on schedule, Matthias.
Yes, I will do my best. So I have a couple of slides, and I basically wanted to update the group on work that has been done by by 85, so the Impact Visual Quality Assessment Group with JVET, which is the group that works on compression and specifically also on like the successor of or potential successors of VVC at this point in time. So we are towards actually issuing a call for evidence as a first step, which means that we would like to see if there's sufficient changes and improvements since VVC to get a new compression standard there. There was a workshop by ITU and ISO in January where this topic was discussed, and where the results basically were that things may point into this direction, but there were also concerns about complexity and things like that, which would be taken into account. And then after that, were quite some discussions of the parent bodies of JVET. So that's SC29 on the ISO side and study group 21 for ITU on what would be potential requirements on that. And then the decision was that we would go for a call for evidence preparation, which then should reflect all the requirements and also contain a meaningful test set. And this aspect of the test set is what I wanted to talk about. So we have came up with a bunch of content categories. Basic dimensions would be SDR content, HDR content, HD and UHD resolutions, applications like streaming and low delay, which would be represented by two configurations, random access and the low delay configurations. Also the consideration of portrait and landscape orientation of the videos. So all these kind of things. And then the consideration of new categories was also considered to be very important, which includes user-generated content, so UGC, and also gaming content, which was not so much in focus in previous JVET developments. So we came up with these 7 categories, which are just short names with different combinations of whatever we have here, with the portrait landscape thingy being mostly in the low delay case and in the gaming and in the user-generated content categories. So the first step in January, we actually already performed on-site experiments. We had collected input for 49 candidate test sequences, which were evaluated at a proposed low and a proposed high rate point. We used the ACR method with the 11-grade scale and had 3 test sessions, 24 experts. That was actually quite a smooth and I think also successful activity, just showing what came out. So the idea was that we would like to identify which sequences would be suitable for the task, and at the same time how suitable was were the points that were proposed. And you see here 2 examples for 4K, so UHD, HDR content, and the 8K crop, which is also something that we did not so far consider for preparation. And then you see the scale, and you see, for example, like for this example, for this Amsterdam sequence, apparently people were not able to see much. Here for another example, the Bode Museum, there were maybe qualities were a bit too low. So there was quite some indications that were given, and out of the set of 49 sequences, we came out with 35, which are listed here. So dark green would mean that those were recommended, light green were considered, and the red were basically removed from the candidate set, which led to the fact that we still didn't have enough because, for example, like here in the low delay case, we only would have 2 sequences, same here in HD, and so forth. And then what was done then in the next effort was preparations towards an ad hoc group meeting that we had in March in Aachen, actually, with on-site expert viewing again. We got another 28 test sequences that were proposed. Partially, this was actually quite new content that was prepared for the task. For all those sequences, we repeated the ACR experiment for those sequences, just to have a consistent set of data. And then we did a larger effort to determine what rate points and what sequences ultimately would be used for the CFE. And the major task is, or the issue is, we do not know yet what kind of qualities the encoding schemes that are submitting will be providing. So we want to have a meaningful coverage of the quality range. We'd like to have 4 test points for evaluation. We need to leave some headroom over the anchor so that proposals may be demonstrating their performance even at the highest rate point, so that you would not run into saturation. We would like to leave enough room at the low end, so the anchor may be actually quite bad at the lowest rate points, and then we would have some clearly distinguishable points in between. So what we did for this effort was to evaluate the VTM, so the VVC reference software for the anchor, and the ECM, this is the exploration software of JVET, as an example for how a relatively high-performing enhanced compression scheme may look like in terms of performance. And then what we did for this task was something that I call a succession test for the VTM and the ECM streams, where we did something like a relative DCR. So we always would compare 2 neighbors starting from the original. Then you would see the highest quality. So you can do a comparison between those 2, and then you would go from the highest quality to the next one, to the next one, and to the next one, and so forth. And so the experts that were in the task were in the test were asked to score whatever they see relatively. So and we wanted to make it rather simple. So we asked them to do a 3-value scale where we would say a +1 would mean the quality of, let's say, the lower one is too close to the higher one. 0 would be okay, and -1 would be a too large step. That was the approach that we took, and then we looked at the average of that. That's I'm calling that a MOS here, and then we looked at a let's say a relative number of cases. This I call this RDIF to compute something like a confidence. So we were not so sure if conventional methods would help here. So we basically looked at how much differences did people see relative to the number of scores, and then how does it relate to the MOS, and we normalize it accordingly. So if both would be in line, then there would be a very low number. That would be high confidence. If it goes towards 1, then it would be a low confidence. And out of that, we looked at we derived some updates for the quantization parameter selection so that the rate points would be adjusted. And so here are just 2 examples of what might have come out. So these are just 2 sequences, and so you would see here this value. So apparently the first point was a bit too high, and then the next step was a bit too large, and so forth, right? And you see then basically by this value for the confidence that people had, they were not super confident for the first one, but then at some other points they were quite confident. And for the second example, this was one where people were quite sure, and we see that the numbers are by tendency quite high. So this probably means that the quality overall was not covering the full range, but was staying at somewhat high quality levels. So that would definitely need or indicate some changes in the proposed QPs. So out of this exercise, so people saw a lot of those sequences. We then collected a reduced set of test sequences, and then that's basically the one that you see here. And then we did a final test in this ad hoc group meeting with a DCR of HD resolution sequences, where we included some new candidates and some of the UGC sequences. And the idea or the questions that we wanted to answer is, did this method result in meaningful rate points for the purpose of the call for evidence? And then we also wanted to learn a bit about how the UGC may behave, where we would have not the compression of a uncompressed source, but of a compressed source, right? So this is the idea, since many applications have this kind of task there. And so just one quick example of results. You see here on the left, this is a UGC sequence. You see here the rating of the uncompressed on the just the ability to distinguish that from itself, right? And people were able to do that for the sequence. And then you see the example for the VTM, the ECM. You see that the range for this one, I think, is actually quite good. For the second one, it's also still good. Maybe one would like to lower the lowest rate point a bit to get a good coverage, and maybe lift this one up a bit so that the quality range would be covered well. And so out of that, there was a issued draft CFE, which is available publicly, so you can download that document from the JVET site with a total of 30 test sequences. There are 2 tracks now in the draft CFE. One is on improved compression performance. One is on encoder complexity, because that was identified to be a key topic, as I mentioned before. So while for the first category, the goal would be the classical one, so we would strive to get significantly better compression performance at the same bit rate. The second goal would be to get comparable performance, or maybe even better, at a lower computational load, specifically at the encoder side. And those are the 2 targets which are currently evaluated for the CFE. And what we are now doing is we are planning for a dry run experiment. We actually had an intergroup meeting just 2 hours ago today on this topic, preparing for checking out those test points that we have designed, and then seeing if it works out, so that we can actually receive the results in October, right? So this is basically where we are. So the setup has been done: 7 content categories, 30 test sequences, 2 tracks. There will be a report on this from 85, which is currently under preparation, just summing up all the activities that have been done. So we did a lot of steps. The main or one driving force was that we were tasked to do the whole setup in a very short time frame, and I think we are actually on a good track to achieve that goal. So out of the July meeting, there should be the CFE issued. Then the responses are expected in October, and there will be an expert viewing fest in Geneva, where we will evaluate at least a big portion of what is going to be submitted for this CFE. And if that whole activity turns out to be successful, then there is a potential development towards a call for proposals for a new standardization activity, where probably the test dimensions and the size and the sequences would be similar to what we are using in the CFE. And at that point in time, probably we will have the laboratory test will be required instead of on-site expert viewing. So that's an activity which I think I mentioned that in previous meetings already. I probably will approach people here quite soon, because we will need a lot of laboratories to cover all these testing activities. And then as the final slide, just doing some advertisements. Please all consider to come to the Picture Coding Symposium. You can consider still to submit special sessions. Maybe you would like to approach Patrick, who's in the room, who's one of the special session chairs. Work in the area of quality is highly appreciated here. And I would love to see you all in Aachen. And that's it from my side. Thank you very much for your attention.
Matthias, thank you. You have quite a few friends of PCS here in the organizing, so please contact.
Yes, I should mention that I'm talking to one right now.
Yeah, and we have time perhaps for one question for Matthias. Come on.
Nobody else? No. Matthias Patrick speaking. Maybe I missed something. It's about the to select these different points. It's per content, and you have to select one anchor recipe.
Yes. So the
but because you are comparing different things, so you select.
You're selecting QP. Indirectly, you're selecting bitrate, right?
Yeah, but my question is that if you have different encoding recipe, because it's call for evidence.
There is no encoding recipe. As you understand, in standardization, it's like a very standard fixed QP.
But still, it's new techniques or new tools you want to try, right?
Maybe I should have explained that a bit more. So the whole effort that we did was to identify target bit rates. So ultimately, the proponents don't get a QP or whatever. This is totally up to the proponent. The proponent gets a number of bit rates, and they would say maybe code this content at, let's say, 800, 1600, 3000 something kilobits per second. And with your method, under the constraint of doing the random access, which would then say, okay, you need to be able to jump into the stream after 1 second each, or something like that. So that's what we ultimately do, and we want to do that in a way that we cover the quality range with those target rates that we have selected.
But this might depend on the proponent, right? You still need a kind of So my question is that it's per content, and this could be also per proposal, that you need to identify this QP point.
Well, the information on the QP point will be available to the proponents so they can see what has been done, for example, for the reference. But for their own scheme, they are free. And the only question that we want to see to be answered is, if you get the rate budget of the anchor of the VVC scheme that we use right now,
Okay.
how much better are you?
Okay. Okay. So the anchor is VVC stream. Okay. So
Exactly.
I got it. Okay. And don't you think there is a risk that maybe we are operating in a range where you may miss the interesting range of one proposal acting like that?
Well, I hope not. So that's why that was so the design goal was that we would have enough headroom at the highest rate point. So the VTM would be still challenged, but a proposal may be much better. You know, in the range of conventional video compression, or maybe also learning-based, I guess, I do not expect that a proposal coming that would be saving 60% of the bitrate or so.
The question is because you have also different type of content now. You introduced and that might change a bit the game for some of them. No?
Yes, sure. Yeah, I mean it will be a big effort, and also well, analyzing the results will be very interesting. We have to be careful, of course, not to draw wrong conclusions from whatever we get out there. But the premier goal first was to have a good diversity of contents that covers good examples for important applications, and then to have a challenging set of bit rates so that we can see if potential candidates schemes would be providing some better performance than whatever we have currently on the table. And the anchor is VVC because it's the most recent standard that has been developed by that community. And this ECM, this exploration model, is just an example. I mean, it will also be part of the CFE, of course, because we want to know what the group has produced in that regard. But it's not an anchor in that sense, because it's not something that has been standardized in any way. It's more like a collection of tools.
Okay. And a quick comment. Be sure I have already proposed to the VQEG chairs to have something in line with for the PCS, and eventually an intermediate meeting, because we have also PCS will be twinned with VCIP, which will be held in Klagenfurt. That was a former meeting venue for VQEG. So I think it could be interesting to do something. Can you remind us the date between VCIP and PCS?
So VCIP is, I think, just 1 week before PCS. So I think it's starting on the 1st or on the 2nd of December, and it's going until Wednesday or Thursday, and then at PCS we will start on Monday. So you can spend the weekend in one of the two cities or somewhere in between, maybe exploring more Christmas markets or whatever your goals might be.
Okay. Yeah, thank you. Matthias, just a very quick, like 10-second comment. Thank you. I think one class of content that is not entirely covered is the new Gen AI content. So I strongly suggest you revisit. This is picking up significant popularity. Number two, really, I applaud the choice of having that bullet that you said about producing a lower complexity model. I think that's a very, very critical. Number three, is this content publicly available, or it's going to be under the usual or sometimes complicated MPEG license?
So it's JVET. It's not MPEG alone.
JVET, yes.
So it's maybe a little bit easier, but for the content, if you're a proponent, you will get access to that.
Okay. Thank you.
There's a typical difficulty, as you say. Some of the content, unfortunately, is not super public, let's say. So that makes it generally a little bit more difficult. But there's also something that we are looking at in 85 to maybe be able to put more stuff into public, also from this side.
Thank you. Thank you again for staying up late. Appreciate it. In the interest of time, we adjourn.
Okay. So enjoy the meeting. I'm actually, it's very sad not to be with you. I would have loved to come, but it was not possible.
Maybe next time. Thank you, Matthias.
Thank you.